Boa tarde a todos presentes e a todos que estão nos assistindo via YouTube. Meu nome é Rodrigo Nemmen, eu sou professor no Departamento de Astronomia do Instituto de Astronomia, Geofísica e Ciências Atmosféricas da Universidade de São Paulo. E vamos dar início à defesa de doutorado do candidato Fabio Muffo Cafardo. O título da tese de doutorado é Explorando o Sagitário A estrela em raios gama com o telescópio Fermi, da qual eu fui o orientador. Essa defesa de doutorado, ela será, como de costume, inteiramente online, seguindo as recomendações da Universidade de São Paulo, a fim, é claro, de evitar aglomerações e assim maximizar a segurança de todos nós em relação à pandemia que ainda está acontecendo. O candidato terá o máximo de 1 hora para fazer a sua apresentação, que será seguida pela arguição dos membros da comissão julgadora. Os membros da banca julgadora são a doutora Regina Caputo, da NASA Goddard Space Flight Center, o professor Jack Hewitt, da University of North Florida, o professor Aion, da Escócia, Melo Viana, do Instituto de Física de São Carlos, da USP, o professor Gastão Cesar Bierrenbach Lima Neto, do nosso Departamento de Astronomia aqui do IAG.USP, e o professor Eduardo Cypriano, também do nosso departamento. Eu gostaria de pedir a todos que desliguem seus microfones durante a apresentação do candidato, por favor. E agora, como é uma defesa bilíngue, eu vou fazer a introdução em inglês. So let's begin the PhD thesis defense of the candidate Fabio Muffo Cafardo in the Astronomy Department of Instituto de Astronomia, Geofísica e Ciências Atmosféricas of University of São Paulo. The thesis is entitled Exploring Sagittarius A star in Gamma Rays with the Fermi LAT Telescope, which was done under my supervision. This PhD defense will be entirely online, following the social distancing recommendations of the University of São Paulo, in order, of course, to ensure the safety of us all with respect to the pandemic. The candidate will have 1 hour for the oral defense. It will be followed by questions from the thesis committee. And I would like to ask everybody now to please turn off your microphones during the oral defense. And now I will give the online floor to the candidate. So Fabio, you may begin your presentation and begin sharing your screen.
Okay, thank you, Rodrigo. Please just let me know if you can see my screen before I start.
Yeah, I can see your screen.
Okay, thank you. So I'll start. Hello, everybody. Before I start, I would like to thank the members of the committee, not only for being here today and for reading my thesis, but also for the contributions you gave me in the last 4 or 5 years. I was fortunate to have the opportunity to discuss this work with all of you, even though briefly in some cases. You were very kind, you gave me very fruitful advice and comments, so thank you very much. Here in this work, I show you almost 5 years of work under the supervision of Professor Rodrigo Nemmen, studying the gamma ray galactic center point source detected with Fermi LAT Telescope. Here is an agenda for this presentation. I will start with an introduction, then I'll discuss our data and methods. Then I'll discuss our results. I'll show and discuss our results, and I'll finish with our conclusions. So every massive galaxy has a supermassive black hole in its center. They manifest themselves in a myriad of different and complex ways. The majority of them is in a quiet state, but others are really conspicuous and detected as activity galactic nuclei. Sagittarius A star is the closest supermassive black hole to us at the center of our galaxy. And like most of the supermassive black holes, it is in a quiescent state. Given its proximity, it is, of course, a very attractive laboratory to investigate in order to understand quiescent supermassive black hole activity. Sagittarius A star is detected in most of the electromagnetic spectrum, but there is still no definitive association between the gamma rays coming from its direction and Sagittarius A star. So understanding its gamma ray emission can give us information on the high energy processes in the vicinity of this supermassive black hole. It can also help us test hadronic and leptonic models for this kind of emission, since they have different observational signatures. And finally, it is also a window into particle acceleration. As I said, there is a gamma ray point source observed by Fermi Telescope coincident with Sagittarius A star. And in this work, we aim to characterize its position and extension, study its flux variability, and measure its SED in the energy range covered by Fermi Telescope, in the GeV energy range. So the central 1.5 parsec of our galaxy is a mostly ionized low-density cavity. It is pervaded by Sagittarius A West, a region of gas composed of filaments, and also a concentration of extremely hot gas that is detected in X-rays. At 1.5 parsec from the galactic center, there is a sharp transition between the central cavity and the circumnuclear disk. And the circumnuclear disk has a radius of 1.5 to 4 parsec and is comprised of orbiting dense molecular clouds and warm dust. Not only gas inhabits the circumnuclear disk, a dense star cluster, shown here in gray, this gray hue here, is also found in the inner parts of the galaxy. The stellar density inside this cluster increases inwards to within the galactic center. In the inner arc second of the galaxy, shown here in the tail, there is a concentration of stars, the S star cluster. The nuclear star cluster is one of the highest concentrations of massive young stars in our galaxy. Beyond the east edge of the circumnuclear disk and outside this image that you can see, lies Sagittarius A East. That is a young supernova remnant. And also the galactic center region is surrounded by several massive and dense molecular clouds with scales up to hundreds of parsecs. The galactic center is the brightest region of the gamma ray sky. In this figure, we show 5 years of Fermi LAT observations of the whole sky in energies above 1 gigaelectron volts. The galactic center is located at the center of this image, somewhere around here. The most prominent feature in this image is this bright band of diffuse emission, which marks also the central plane of our galaxy. This is the result of cosmic rays collisions with the interstellar gas that lies in the galactic plane. The galactic center is embedded in this gamma ray component. In the most recent catalog of Fermi sources, there are 36 sources in the inner 3 degrees of the galaxy, which is the most crowded region of the sky. You can have an idea looking for this image, the amount of sources here. From the beginning of Fermi LAT's operation, one of these point sources has been observed coinciding with the position of Sagittarius A star. The galactic center is among the brightest and the most complex region of the gamma ray sky. Other than harboring Sagittarius A star, the inner region of our galaxy hosts ongoing star formation, which provides plentiful cosmic rays and gamma ray sources. So the combination of an extremely large number of sources with considerable diffuse emission makes the galactic center the most complicated region of the universe to work with gamma rays. As I'll explain later, to work with Fermi data, it is necessary to fit models to the observational data. For instance, the models that we worked with took us several weeks each to prepare. We developed several other models than the one that we are going to show you that were not used for various reasons. So it took us considerable amounts of effort. And other than that, some analyses performed with Fermi data are very time consuming. For instance, the creations of light curves that we are going to present in this work took more than 1 month each one to complete, even using a computer cluster. Sagittarius A star is the closest supermassive black hole to us. It has about 4 million solar masses. It is at 8 kiloparsec away from us, and it was originally detected as a radio source in the 1970s. So it is an alluring source for us to study. In the TeV energy range, the HESS and the MAGIC collaborations observe an extended emission centered in Sagittarius A star. This emission was explained as the result of interaction of very high energy protons with the gas content in the central 10 parsecs of our galaxy. And both collaborations also include a point source coincidence with Sagittarius A star in their catalogs. And we can show that, we can see them here marked with stars in these plots. And following has collaboration detections of gamma rays from the galactic center, several candidates have been proposed for this emission. Sagittarius A star itself, of course, a pulsar ring nebula, the supernova remnant Sagittarius A East, self-annihilating dark matter particles, and as yet undetected pulsar, or maybe population of pulsar, among others. The nature of the gamma ray emission from the direction of Sagittarius A star, hence, is still a matter of debate. Its spectrum and variability are so far unconstrained, and the solid association between this emission and the supermassive black hole is yet to be established. In this figure, we show a sketch of Sagittarius A star quiescent and flaring broadband spectrum. Most of the time, Sagittarius A star is in a steady state, emitting about 10 to 36 erg per second between radio and X-rays. On top of this steady emission, Sagittarius A star is highly variable in the infrared, X-rays, and also in longer wavelengths, which suggests a compact source. Here we show images for the red flare ever measured from Sagittarius A star. Here is the flare, and here is the afterglow, and you can see the source fading away. Typically, about, and here I show you one X-ray light curve with a flare. Typically, about one X-ray flare is generated every day with duration of a few tens of minutes. The near-infrared flares are even more frequent, and flares are also observed in longer wavelengths. So flaring emission is an indicative that some accretion, heating, or some magnetic reconnection mechanism has given rise to enhanced emission from the vicinity of the supermassive black hole. The luminosity of Sagittarius A star is dominated by accretion from stellar winds in its vicinity, and in addition, large accretion rates probably occur from time to time due to stochastic density fluctuation in the accretion disk, or when large gas clouds with low angular momentum fall into its center. Although Sagittarius A star exhibits daily flares, it is actually in a very quiet phase nowadays, but there is tantalizing evidence for an enhanced level of activity in the recent past of Sagittarius A star. Su and collaborators, for instance, in 2010, detected two large gamma ray bubbles extending 50 degrees above and below the galactic plane. The Fermi bubbles should have formed between 1 and 3 million years ago during a large episode of energy injection in the galactic center that lasted between 100,000 to 500,000 years. The origin of the bubbles is still debated and could be due to a previous nuclear starburst or some past accretion events of the supermassive black hole. Also, X-ray observations since the 1990s show hefty variations in line emission propagating through molecular clouds in the inner galactic regions. These variations are likely the result of a highly variable active phase of Sagittarius A star within the past few hundred years, which is still echoing through the clouds. In the image here, we can see the line emission in the clouds lighting up through time, and it is compatible with them being excited by X-rays coming from the direction of Sagittarius A star. This is explained by at least two luminous outbursts 100 and 400 years ago, in which the luminosity of Sagittarius A star went up at least 1,000 times. Given the surplus of gas reservoirs in the galactic center region, Sagittarius A star is remarkably underluminous. Its luminosity is 4 orders of magnitude lower than the expected luminosity based on the accretion rate at its boundary radius. An optically thick, geometrically thin disk that is a model successfully used to explain accretion sources like blazars is not compatible with Sagittarius A star's behavior. The observational data of the quiescent state of Sagittarius A star actually favor models in which very little of the gravitational potential energy of the inflowing gas is radiated away. The radiatively inefficient accretion flow models, or RIAFs. These kind of models have been the most successful in fitting Sagittarius A star spectrum and explaining its relative faintness. The Fermi telescope was launched in August 2008. It observes the whole sky every 3 hours. So the combination of more than a decade of continuous observations allows for two complementary approaches to gamma ray astronomy. One is the continuous exposure of the gamma ray sky, allowing for deeper and sharper images, and time domain gamma ray astronomy. And of course, we took advantage of both approaches. The telescope is composed of two instruments: the Large Area Telescope, shown here in black, this black box on the top of the telescope, and the Gamma Ray Burst Monitor. In our work, we used 11 years of observations in the 60 megaelectrovolts to 500 gigaelectrovolts energy range collected by the Large Area Telescope. Of the several sources near the galactic center in the Fermi catalog, the point source with this long name here is the brightest and is the closest to Sagittarius A star. So it is an alluring source to investigate as the possible manifestation of the supermassive black hole in the Fermi LAT energy range. A little bit about production of gamma rays. The most usual starting point for gamma ray production is a population of accelerated charged particles. Near the galactic center, Sagittarius A star is of course a natural candidate as a source of cosmic rays responsible for the astrophysical gamma rays. The mechanism behind the production of gamma rays is different depending on whether the cosmic rays are leptons or hadrons. Relativistic charged particles accelerated by magnetic fields emit synchrotron radiation, and this process is much more important for leptons than for hadrons. And lepton can also upscatter low energy photons, transferring parts of their kinetic energies to the photons. In particular, ultra-relativistic electrons, as shown here in this image, can upscatter photons up to gamma ray energy bands. And the collision of a proton with a target nucleon, as shown here in this image, and this target nucleon could be, for instance, in a molecular cloud, initiates a hadron cascade, shown here with this little dots here. The neutral pion, as a result, pions are created, and the neutral pion decays almost immediately into two gamma ray photons. This hadronic process is very relevant in RIAFs. Since ions hardly radiate, they are heated to very high temperatures, resulting in proton-proton collisions that originate gamma rays. The SED of this radiation has a distinct bell-type shape, as shown here an example, rising steeply in energy below a few hundred megaelectrovolts, and as we can see here in this plot. And this feature is often referred as the pion decay bump, and is used to identify hadronic astrophysical gamma ray emission. Now we move on to the data and the methods. The analysis of Fermi LAT data starts with the data selection, which includes the energy range, the time range, the position of the sky you are interested in, the size of the region of the sky you are interested in, and also choices regarding the quality of each event detected by Fermi. So a qualitative exploration of this data will present spatial clustering of photons, which hints for the presence of sources, for an example here. But a quantitative study requires fitting models to the data. This necessity is justified by several reasons. For instance, Fermi LAT's effective area is dependent on the photon energy and the angle of incidence. Fermi operates scanning the whole sky every 3 hours, which results in a source going from unexposed to the instrument to being exposed by several different angles in a matter of just a few tens of minutes. Also, the instrument's large PSF, there is also energy dependent, and the nature of the gamma ray sky backgrounds. So as a starting point for our modeling of the Fermi LAT data, we used the 4FTL catalog of sources created by the Fermi LAT collaboration, and we also considered two diffuse components to the model, the galactic diffuse emission model and the extragalactic diffuse emission model. And to do the analysis, we used Fermi Tools, that is a suite of data analysis software provided by the Fermi LAT collaboration, and FermiPy, which is a Python package that facilitates analysis of data from Fermi LAT. We use the maximum likelihood technique to find the best fit model to the data. The likelihood is the probability of obtaining the data given a specific input model. In our case, the model consists of the gamma ray sources distribution in the sky, including their spectral model and their position. To fit a model, we vary these parameters until the likelihood is maximized. The maximum likelihood method provides the best fit parameters. However, it does not include a measurement of the quality of the fit. The only way forward is to compare different potential models and select the one with the best fit to the data. The rationale behind this is the assumption that a higher probability of obtaining the data from a model signifies that this model offers a better description of the underlying reality than some adversary model. The quality used to select between two potential models is the TS, which comes from test statistic. So suppose we are interested in evaluating the existence of a source that is not currently part of the model. We just maximize the likelihood for a model without the additional source and for a model with the additional source included, and we apply this equation. Thus, a larger TS indicates that the null hypothesis is incorrect, which means that a new source is a better explanation in this example. And as a general rule, the square root of the TS is approximately the value of the significance of the preferred model against the alternative model. And to obtain good models, we needed several rounds of fitting. After every round, we evaluated the quality of our results using different diagnostic tools. Here, I show you the residual maps. They are built by subtracting modeled counts from the real data and searching for regions with significant residuals. Positive residuals in these maps indicate regions that are underpredicted, whereas negative ones indicate overpredicted regions. The TS map, or another diagnostic tool that we use, are constructed by moving a putative point source through the region of interest and performing a maximum likelihood at each point. High values in these maps are indication of regions where sources are not well modeled, where new sources should be included in the model. So maps similar to the ones shown here were generated and evaluated for all the models that we used at every fitting step of our analysis in order to identify sources or regions that demanded further fitting. With the goals of taking advantage of Fermi LAT's better PSF at higher energies, and also to evaluate the impact of photon energy on the source position, we divided our analysis into energy bands. So we started with a model that we call the universal model in the 100 megaelectronvolts to 500 gigaelectronvolts energies. And then we divided this model into three other models with energies from 300 megaelectronvolts to 3 gigaelectronvolts, from 3 to 10 gigaelectronvolts, and from 10 to 500 gigaelectronvolts. And we used a method that we call the minimal fitting to create these three models. And finally, we created a model in the 6 to 300 megaelectronvolts from scratch and totally independent from the universal model, shown here in green. We use different choice of parameters for the models, as shown here, and further described in the thesis. We use the universal model to obtain the source's gamma ray luminosity, its light curve, and its SED. And also we use the other models to evaluate the source's position as a function of energy. And to localize the source, we use Fermi-Pi's extension model method. It scans the TS map around the source position, searching for a peak in the likelihood surface. To measure the variation of flux of the source in time, we use Fermi-Pi's method light curve. This method fits a source, just like we described it here, but now in a sequence of time beams. So, and after obtaining the light curve, we searched for variability using several different approaches. And we use Fermi-Pi's SED method to create the SED. The process is very similar to the one used to create the light curves, but now instead of separating the data into time beams, we separated them into energy beams channels. And now our results and discussion. A result from the fitting process is the photon and energy fluxes of the source, and here are the values we obtained. Assuming a distance of 8 kiloparsec away from us and isotropic emission, this energy flux measured in the 100 megaelectronvolts, 500 gigaelectronvolts, this energy flux here, corresponds to a gamma ray luminosity of 2 × 10⁻⁶ ergs per second. And this luminosity is comparable with Sagittarius A star bolometric luminosity that is of 10⁻⁶ ergs per second. The position of the source is consistent within 1 sigma of Sagittarius A star's position in the energy ranges 60 to 300 megaelectron volts in green and 10 to 500 gigaelectron volts shown in gray. If we consider only the 3 highest energy bands here, the gamma ray centroid approaches Sagittarius A star, shown in black here in this image, as the energy increases. The same can be seen here. So it approaches Sagittarius A star with the increase in energies. The projected distance to Sagittarius A star as a function of energy is smaller than about 4 parsec for these 3 highest energy bands, which suggests that the cosmic rays are originating, that originates this emission, are coming from the surroundings of Sagittarius A star. The emission centroids are compatible with the gas distribution in the inner parsecs of the galaxy. This coincidence may indicate that the gamma ray arising from the galactic center is due to hadronic processes. The strong similarity between the electromagnetic energetics of the source and Sagittarius A star, combined, of course, with the positional coincidence, suggests that the gamma ray point source investigated in this work is associated with the supermassive black hole. But the upper limits of 0.24 degrees for the central source extension corresponds to more than 35 parsec at the distance of Sagittarius A star, thus allowing for several other potential candidates for the gamma ray production site. So this leads us to this question: can this gamma ray emission be explained by anything else other than the supermassive black hole? And now we discuss the most promising candidates for this emission and compare their characteristics with our observations. The first candidate is Sagittarius A East. There is a supernova remnant located in the inner parsecs of the galaxy. It was proposed as the source of the TeV gamma rays from the galactic center, but our results show the origin of the emission above 300 megaelectron volts. So these 3 dots, these 3 emissions here, coming from a region where Sagittarius A East flux is comparatively low and significantly displaced from the radial maximum. The radial maximum from Sagittarius A East is somewhere around here. So the emission is displaced from that position. And the same argument was used to rule out an association between the very high energy Hess source, shown in yellow in this image, and the supernova remnant. So this can be used to rule out these candidates. Another candidate is self-annihilating dark matter particles. They are often used to explain the galactic center gamma ray excess. There is a surplus of gigaelectron volt emission, diffuse emission, that cannot be explained by known sources, but it is not a satisfactory explanation for our source of interest because it is a point source, while the dark matter emission is expected to be spatially extended. The gamma ray spectra of pulsars and millisecond pulsars can be described as a power law with an explanation cutoff above only a few gigaelectron volts. Also, the Menezes and collaborators studied the gamma ray emission of all globular clusters in the Milky Way. This emission is attributed to their large population of millisecond pulsars, and the Menezes and collaborators found no significant flux above 10 gigaelectron volts from the globular clusters. In contrast with that, the galactic center point source is detected at energies above that. So we can rule out a population of pulsars or a single pulsar in the line of sight as the explanation for the point source we are studying. As the fourth candidate, we consider the possibility of a background blazar that is fortuitously aligned with Sagittarius A star as the explanation for the central gamma ray source. The energy flux we measure for the central source would put the hypothesized blazar among the 0.2 brightest blazar in the 4 FGL catalog. Here are all 4 FGL cataloged blazars. So the combination of 3 very unlikely events, a blazar that is atypically bright in gamma rays, that is also unusually dim in other wavelengths, actually so dim that it is undetected in other wavelengths, and that is perfectly aligned with the galactic center, would have to be acting in concert to explain the central source as a blazar, which is very unlikely. So we can rule out this candidate. But we have favored candidates. Prominent gamma ray emission from mega electron volts to tera electron volts energies coincident with Sagittarius A star position is observed not only by Fermi LAT, but also with other gamma ray observatories. Since the beginning of Fermi operation, there is a point source that is coincident with the position of Sagittarius A star. This source was studied by Chernyakova and collaborators in 2011 with 25 months of Fermi observations, and also by Malyshev and collaborators in 2015 with 74 months of data. Aion and collaborators collected several models for this emission from Sagittarius A star, and we call them the Fermi era models, since they were all created taking into account Fermi LAT data. We show here an image from Aion et al. Kuzonoz and Takahara is one of these models. It is a leptonic model in which electrons escaping from the vicinity of Sagittarius A star accumulate in a region with a size of 0.3 parsec, where the gamma rays are produced by inverse Compton scattering of soft photons emitted by stars and dust around the galactic center. Another leptonic model is from Malyshev and collaborators. Their model is not shown here in this image, only their observational data in red. This data is from Malyshev et al. It is also a leptonic model, and they propose a combination of emission from electrons injected during a strong Sagittarius A star flare that occurred 300 years ago. I showed you the X-ray flares echoes from this emission, with emission from much weaker and more recent activity as the source of the gamma rays. There is a leptonic model from Chernyakova and collaborators. Its hadronic model proposed that relativistic and no relativistic protons, presumably accelerated near Sagittarius A star, interact with the gas in the inner parsecs of the galaxy. And Linden and collaborators developed a very similar model. Another hadronic model is proposed by Fatuzu and Melia, where they consider a two-phase environment surrounding Sagittarius A star, an inner high-density torus, and the surrounding interstellar medium filled with shocked stellar winds, which they call the wind zone. And the Fermi gamma rays would come from the torus, and the higher energy photons would come from the wind zone. Gu and collaborators propose a hybrid model. In their scenario, protons and electrons are accelerated in the galactic center, possibly around Sagittarius A star. And collisions between the protons and the interstellar gas would produce the TeV gamma rays, and electrons would inverse Compton scatter the soft background photons, producing the GeV emission. All these Fermi era models are consistent with our observations, except in the lower energy band that we use. I'm going to show you later an image with our SED. Here, I'm only talking about the energy flux. So it is, these models are not just coincident with the low energy band that we use. This energy band is the most subject to source confusion and to the impact of the galactic diffuse emission. So it is an energy band harder to work with. And here I show you the resulting SED from our work. It was created with the universal model in the 100 mega electron volts to 500 gig electron volts energy range. And here we compare the galactic center sources SED with the Fermi era models already mentioned. So we replaced Malyshev's data with our data here. So this is our data. Our SED is compatible or close to compatible with all models in the 2 or 3 gig electron volts and 500 gig electron volts energy range. At lower energies, they depart from the Fermi era models, but it is important to note that these models were constructed around Fermi LAT data obtained during the second catalog period, or even before that. And our data is more recent with better galactic diffuse emission models and updated Fermi tools, etc. But other than trying to find models that fit exactly to the data, we are also interested in observing the shape of the SED, because as I mentioned, every hadronic model exhibits a low energy cutoff, and it is expected because of the energy threshold of the pion decay bump. And this feature is very clear in our data. This SED shape is reported for the first time for this galactic center Fermi source in this thesis, and is a strong evidence of a hadronic origin for this emission. The pion decay bump is a signature expected in RIAFs. In these environments, the protons are heated to very high temperatures, which leads to gamma ray emission from proton collisions. And for several decades, RIAFs models have been successfully used to explain Sagittarius A star observations. And our results fit nicely with this framework. The shape of the SED is compatible with the ones expected by the hadronic models, as we show here. We are highlighting a characteristic hadronic and a characteristic electronic model from the Fermi era models. And here we show that the characteristic hadronic model in red has a shape very similar to the SED that we obtained. We are still working on further analysis to confirm these results, and we will report them on a forthcoming paper. And now we talk about the light curves. In this figure, we show the 15 days beams energy and photon flux light curves. We compare these results with the mean flux and with a 5-day rolling average flux, average of the flux, and we found no signal of flaring. We also checked if the variability observed in these light curves arises from a random process. And to do that, we tested if the flux distribution is compatible with a Gaussian, which is representative of a normal random process, or if it's compatible with a log normal distribution, which is consistent with a flaring source like blazars. And our results indicate that the source flux distributions are indeed compatible with a Gaussian, which means that the variability likely arises from a random process. This alone, of course, does not include the possibility that the source, although in a steady state most of the time, has very short periods of variability. The flares from Sagittarius A star in longer wavelengths are frequent. They are typically daily in X-rays and even more frequent in near infrared. And also they have very short duration, lasting usually for tens of minutes. So if the same processes that they generate them are also generating gamma ray flares with similar rate and duration, these flares could not be identified with 15 days light curves, 15 days beams light curves. So in this figure, we list a few examples of remarkable events that could enhance the gamma ray emission from the galactic center, like flares in other wavelengths and orbital ephemerides, and there is no notable variability in the source's energy flux associated to them in gamma rays. Finally, we tested the presence of a global trend in the 11 plus years of data collection that we used. We simply fitted linear functions to the observed data, and the light curves are compatible with constant flux for the duration of our observation. So the results obtained for the 15-day beams light curves are that very few time beams have a significantly incompatible flux significantly incompatible with the average flux. The flux distribution is compatible with the source's flux being generated by a normal random process, and also there is no signal of a global trend in the data. Now we compare all of our observations with previous observations done with Fermi. Cherniakov et al., as I mentioned, worked with 25 months observations of Fermi LAT source. They used the first Fermi catalog, the source in the first catalog, and also they use HES observations. Their analysis of the Fermi data did not uncover any statistically significant variability for the source at gigaelectron volts energy on 1 month time scales. And this is compatible with our findings. Our results are also compatible with Malishev and collaborators' observations of the galactic center source in the second Fermi catalog. They found no temporal variability on year-long time scales in the 1 to 10 gigaelectron volts energy range that they used. The steady emission is a characteristic of the gamma ray flux from the galactic center. In addition to this Fermi LAT data, the same is true for higher energy observations. In summary, no variability has been detected yet in Fermi LAT energy levels and above, and this includes our observations. And now we compare the variability that we observed with what is predicted by the Fermi era models. So they try to explain the Fermi galactic center source as the manifestation of Sagittarius A star, and most of them were created taking into account the temporal behavior. So we discuss that now. Cherniakova et al. Hadronic model consider an emission region as large as a few tens of parsecs, much, much larger than the region from where the X-rays and the near-infrareds come from. And for this reason, they do not expect variability in gamma rays in time scales below a few tens of years, which is the light crossing time of their emitting region. And this is compatible with our observation. Since electrons have much shorter cooling time than protons, the use of leptonic models to explain a steady source is challenging. Kuzonoz and Takahara proposed a leptonic model in which relativistic electrons supplied by flare events that occur near Sagittarius A star accumulate in a region with a size of 0.3 parsec. In their model, the electron cooling time is longer than the escape time, which justifies their steady-state homogeneous model. And also, since the flare intervals that accelerate the electrons are of only a few hours, they assume a continuous injection of electrons in their model, which corresponds to no variability expected. Fatuzzo and Melia proposed another hadronic model. They assume a steady-state ejection of particles from Sagittarius A star and an emitting region of a few parsecs. And they conclude that the Fermi and the Hess data that they studied do not provide evidence for variability from Sagittarius A star in high energies. Gu et al. Proposed a hybrid model where both electrons and hadronic cosmic rays were accelerated during a past event of activity of the galactic center about a few hundred years ago, that same one that I showed you before from the X-ray echoes. And they do not expect significant gamma ray variability in time scales smaller than about 100 years, which is consistent with our results. Malishev and collaborators proposed a leptonic model for the source, and in there they used 6.2 years of Fermi data observation to create their models. For longer time scales, they made a testable prediction of a 5 to 10% decrease in the 1 to 10 gigaelectron volt flux in a 10-year time. Here I show you their light curve with 1 year beams. Our 11.3 years observations in the 3 to 10 gigaelectron volts are not compatible with their prediction because it shows no signal of a trend as expected by them. So models for the emission above a few megaelectron volts from the galactic center must take into account that this emission shows no temporal variability. All these Fermi era models were created in this context, including hadronic and leptonic and hybrid. This shows that a myriad of models can explain the lack of variability in the gamma ray from the galactic center gamma ray emission. And now we go to the conclusions. The spatial coincidence of the galactic center Fermi source with Sagittarius A star is a necessary but not sufficient condition for it to be considered the counterpart emission of the galactic center supermassive black hole. In this respect, our imaging analysis showed that the source position is coincident with Sagittarius A star in the 60 to 300 megaelectron volts and in the 10 to 500 gigaelectron volts energy bands. And the gamma ray emission is also consistent with regions very rich in gas. And when we consider only the 3 highest energy bands used in this work, the emission centroids approach Sagittarius A star position as the photon energy increases. Furthermore, the source's luminosity is similar to Sagittarius A star bolometric luminosity. The temporal analysis showed no variability in 15 days time scales, and the light curve is compatible with the Fermi era models. And the SD shows a signature of a hadronic scenario and is also compatible with the Fermi era models. Taken together, these results support the picture in which the point source that we observed with Fermi at the galactic center is the manifestation of the Sagittarius A star in the megaelectron volts to gigaelectron volts energy range. A hadronic model in which the accelerated protons interact with the gas content of the galactic center is the most suitable, because it naturally explains the steady light curves and the shape of the observed SED. And it is also compatible with the emission positions and extension upper limits. And now we talk a little bit about future perspectives. First, let's talk about ways we could improve our work. We are working on further analysis to confirm the pion decay bump of the SED and also to estimate the systematic uncertainties of our results before publishing them in a forthcoming paper. We also plan on developing our own emission models based on the SED we obtained. About future missions, the only way to obtain light curves with time beams that are short and also have high enough TS is to collect a large number of photons. Our results are very, very close to Fermi LAT limits, which is governed by its effective area and sensitivity. The ground-based gamma ray observatories have much larger collecting areas, but they are localized in regions with low exposure to the galactic center, with the exception of HESS. CTA South, that is located or will be located in the Paraná Observatory in Chile, will have very good exposure to the galactic center. Upcoming gamma ray space observatories like Amigo will cover energy ranges that overlap with Fermi LAT's low energy limit, bridging the gap to the current generation of hard X-ray instruments. As Fermi, they will cover the whole sky periodically, being constantly exposed to the galactic center, which, combined with their high sensitivity, will potentially allow light curves with higher temporal resolutions. The new generation of gamma ray telescopes will also have a positive impact on the imaging, positional, and extension analysis that we performed. CTA will allow studies in spatial and spectral details that is unavailable today, with arc-minute resolution at energies above Fermi LAT's operational range, potentially enabling a firmer association between the very high energy point source in the galactic center with Sagittarius A star or with some other nearby candidate. CTA will be able to enhance significantly the assessment of the morphology of the TeV source, which will allow for correlations with the gas density distribution in the galactic center. This could potentially confirm or deny the hadronic origin for the very high energy gamma ray emission. And even closer observations of Sagittarius A star are still anxiously anticipated. As an example, we mentioned the results of the Event Horizon Telescope that will reveal the image of the shadow of Sagittarius A star on the accretion flow, and also the extremely large telescope will increase the probability of finding S-star cluster members very close to Sagittarius A star with near-infrared observations. And now I let you with a few highlights of our work. The recent history of astrophysics is brimful of discoveries regarding black holes and the galactic center. This thesis is the result of over 40 years of work and is aimed to contribute as a building block to our understanding of those intriguing objects and their role in the cosmos. So, thank you very much.
Thank you very much, Fabio. Muito obrigado. So now we can either begin immediately with the questions, or we can have a 5 minutes break for getting some water. So I leave it for the committee members. Do you want a 5 minutes break, or should we jump to the questions? So Eduardo, you want a 5-minute break? No?
No, you can go on.
Can you go? Okay. O candidato, so first in Portuguese, then in English. O candidato terminou sua apresentação oral. Os membros da banca podem agora iniciar a sessão de perguntas. Cada membro da banca terá um máximo de 40 minutos para interagir com o candidato, fazer perguntas. E, seguindo a tradição, eu gostaria de convidar os membros por ordem decrescente de distância física até o IAG. Então, portanto, a gente vai começar com a doutora Regina Caputo. So the candidate has finished his oral presentation. The members of the thesis committee can now begin with the questions session. Each committee member will have a maximum of 40 minutes to ask questions and interact with the candidate. And following the tradition, okay, so this is a tradition here in our institute. So I would like to invite members by decreasing order of distance from the astronomy department here. And according to my estimates, it's pretty clear that the committee member which is farthest from here is Dr. Regina Caputo. So I invite Regina to begin with her questions. Please, Regina.
Okay, thank you, Rodrigo, and thank you, Fabio. This overall was a very nice presentation. I very much enjoyed it. I think you overall did a very nice job. And I also enjoyed reading your thesis. So congratulations to all of that. So
thank you very much. Sorry to interrupt you, but I
no, it's fine.
Thank you very much.
Of course. And I have to say, my questions stem from like because it was a stimulating thesis and presentation, I'm very curious about these questions. And so one of them was when you were talking, I know that one way that Fermi associates sources is through variability. And so your search of the light curves, I think is very important to this work. And so my question is, given that, Sagittarius A star shows a lot of variability in X-rays and in other wavelengths, but on much shorter timescales than 15 days. Given the energetics of the flares in these other wavelengths, would you expect to be able to observe them in the gamma ray band, given the LAT sensitivity?
Well, we when we started this work, we were hoping we could. that is how we started it. Yeah. And we had some promising results when we were still with the 3FGL, and the first light curves we created, they had some hints of variability of flaring that we were hoping to check if they coincide with flares in other wavelengths. But when we improved our models and we started to make better modeling, this supposedly flaring states, the supposed flares, they vanished. So yes, we were expecting we could, but this is dependent on actually on the origin of the flares, of the flares in X-rays and near infrared. That depends a lot on the models used to explain them. So we were hoping that they could be something possibly connected with a very weak jet from the source, but we couldn't see them. So I think the answer to your question is we hoped to find them, but we couldn't. And so yes, we were expecting to see them.
No, thank you. What was the scale of the variability, or on what time scale was the variability that was potentially observed in the 3FGL?
I think I remember many years ago we started working with these light curves, but they were like 45 days.
Okay.
60 days. So they were, of course, not related to the X-rays and near infrared. If they were like in a single point in a 15-day light curve, for instance, and it was coincident in time with a very high flare in other wavelengths, we could argue for a correlation. But since it was very, they were very long, we weren't. And later they vanished when we improved our model. Yeah. So yeah, make this association.
Yeah. No. I understand. So that's very, very interesting. And so it is nice to see the analysis coming to, I don't want to say conclusion, but just utilizing the full data set. Too bad.
but I think our results they are, first of all, in talking about the light curves, they of course they confirm previous results, but they are more recent. So it's something that must be taken into consideration in the creation of new models for the source. So, I mean, when we the previous light curves we have are much shorter than ours, and we can say that the trends of not flaring emission is confirmed for almost 2 times longer light curves than we had before in the literature. So
no. So then, no, that's really good work. So continuing on this question, could you go back to the slide where you were comparing the light curve of the Malyshev et al. Results to what you were getting?
Just a second.
Yeah, I would tell you what slide, but I didn't write it down.
Yeah.
Oh, no, that's exactly right. And so you had made the comment that you had disagreed with this result.
Sorry, go ahead. Sorry.
Oh, yeah. But I was going to say, it actually looks like, given the green lines and given what you saw, it looks actually like you agree, like just by eye, it looks like you agree with this result.
Well, we agree with this light curve. We disagree with this prediction. They had a prediction that in 10 years, the electrons that they were observing, the leptonic population that were creating this light curve would cool enough so that this tiny trend that maybe you can see in the light curve would be detectable in a 10-year period. And we couldn't see that the emission is constant in 11 years. So
I see.
I think we do not disagree with this light curve. Actually, they are very similar to ours, showing continuous emission. But they were predicting a decrease of 5 to 10%, which we didn't find.
Okay, no, then I understand and I agree with your statement there. Okay, so let's see now, going from the variability to more of the modeling to make sure that you are correctly modeling the point source. So I know that galactic emission models are notoriously complicated because the galaxy is complicated. And so I guess one of the things that I'd like to just understand is, so the galactic emission model that you used, I know that there's quite a bit in the line of sight between us and the galactic center from the spiral arm emission. And so could you just talk a little bit about, what exactly the modeling includes to cover that galactic emission model?
Okay, first of all, the galactic model we are using is the standard Fermi galactic model. Okay, so we did not try, there are a few works with the galactic central source or with the galactic center that uses different models created for their analysis and things like this. We did not use that. We used the regular model. And we also did not do, and it's something that we are planning to do now to create a better SED also. We are planning on using different models, at least to assess the systematic uncertainties caused by different modeling. Okay, we did not do that. We used the standard model that considers mostly the emission from pion decay of the interaction of protons with the gas. But in the thesis, I list every component of the galactic diffuse emission model. I have, I don't know, 2 or 3 pages describing each component. But it is diffuse emission from several sources like Brist-Shalom, inverse Compton. But the most important is the pion decay caused by interaction of protons with the gas in the galaxy.
Okay. Then I think that I just have maybe one more question. I know I'm not going to take nearly the 40 minutes or whatever, and that's okay. And this
that's fine. That's fine. We don't need to take the 40 minutes. It's the 40 minutes. It's a ceiling.
Good. Okay. I'm gonna say that would be really tough. I don't.
It'll be tough for me too.
Okay. Well, and this is just a speculation now that I think you are clearly an expert on the galactic center and the gamma ray emission from this because you've spent so much time thinking about it. And there's lots of different models like this hadronic, hybrid, leptonic. What do you think is making the gamma ray emission that we see?
Well, I think based on the SED and the light curve and our results and the amount of gas in the galactic center, I think that this emission is hadronic. It is. I'm not sure about the origin of the protons that is generating these gamma rays, but it seems to be hadronic. But when we consider the best models in the literature to explain Sagittarius A star in the other wavelengths, the RIAF models, all of them predict sufficient energetic proton population that would lead to gamma ray emission from proton-proton collisions. So everything fits together very well. So the models that explain Sagittarius A star in other wavelengths, the RIAFs predict that we are going to find energetic protons. The light curve is steady, which is predicted also because usually this emission is extended not in the sense of not a point source, but occupies a large area in the universe. The SED shows a signal of a hadronic emission, so I think that is the explanation.
Okay. No, thank you, Fabio. Again,
thank you very much.
Nice job. No, thank you, really.
Thank you very much, Regina, for your thoughtful comments and questions. So now let's move on to the next committee member by decreasing order of distance from the department. So now let's so Jack, please, you can begin with your questions.
Thanks. Before I ask questions, I just wanted to say that it's very, very impressive, Fabio, what you've done here, because this is an extremely challenging analysis to do. And you could have analyzed maybe 3,000 blazars and not have done as much work as this one source.
Thank you very much. Thank you.
So I just had a couple of questions about, mostly about the diffuse emission and looking at the sources. So I forget if you showed these in your slides, but I know in your thesis, figures 2.3 and 2.4 and in Appendix H, you show the residuals in your analysis region.
I think I have a slide with that. Let me see if I find it. It's not going to take a while. I think you're talking about this image, right? Can you see? You're talking about the residual
exactly
map?
What I was thinking about. And so if in your histograms of the residual significance, there's an offset.
I have the histogram here also. I'll show so everybody can follow. But go ahead, continue.
So can you explain why there's particularly in the, I think it's this energy band, yes, 300 to 3. Yeah. This is clearly there's a skew towards positive residuals. And so can you explain this? Could this be due to unmodeled sources or diffuse emission, or is this unexplained?
No. I have a few explanation for this. The major reason for that is, of course, modeling that is not great. Okay, we can see here from this residual map that we have a few areas like this black one with significant residuals in black here. They are mostly associated with the galactic plane shown by this line here. So it is probably a region or a model that is not very well fitted to the data, but there is a reason for that. When we started this analysis, we separated this analysis in 4 totally independent models, okay? So we had one in the 60 to 300 megaelectronvolts, another one that we started from scratch in the 300 to 3 gigaelectron, 300 megaelectronvolts to 3 gigaelectronvolts, and so on and so forth. And we created them from scratch. And later, just because we wanted to see the source position in different places, changing with energy, okay? We wanted to see if all of them were correlated to Sagittarius A star. Maybe some of them could be correlated to some other source or closer to that other source. So it was an initial investigation. But these models had a problem that I think I have a slide here that I can show. Since we created them individually, when we observed the other sources in our region of interest, their spectral models were not continuous, okay? Because they were modeled independently from one model to the other. And then we got a suggestion that I'm not sure if it came from New Jack or somebody else from the collaboration. So here is what happened when we were working with 4 different models. This same source, for instance, had one spectral model in the Zener. We were using a power law for it, okay, to model it. But it was here in this energy band, here in this other energy band, and so it was not continuous. And we were, of course, not happy with that. So somebody suggested, why don't you start with a universal model and you split it with the minimal fitting you can make, okay? So so the sources are continuous in all different, in the 3 different energy bands that you're using. And that's what we did. So, but when we do this, and this minimal fitting, just for you to know that, it is in the thesis, but I think it's important to explain here. In this minimal fitting, we started with this model, we separated the energy bands in these 3 energy bands, and we just fitted one time the normalization and index of this source, that is the source that we are studying, the normalization of the galactic diffuse emission and the isotropic diffuse emission. But this, of course, you can see from that residual map, that it is not enough to create a very good model, a very well-fitted model to the data. So this is the explanation for that. But we tested and since we just use this analysis for the positional work and just to have the flux in these 3 energy bands, we tested if this could lead to results that were very wrong for some reason. So we compared with that 4 model with that 3 model that we created from scratch, and the results regarding the flux, the energy and photon flux, and the position of the source were coincident in within 1 sigma. So we said, okay, this model is not perfect, but it results is pretty compatible with results that we obtained in the same energy range, but with model that we started from scratch. So I think I explained more than you asked. So I explained the origin of the problems in the maps. And I also explained that they didn't have huge impact on the results that we got. Okay?
Yes, that's great. So maybe you can tell me more about your plans to develop your own emission models to explore the systematic uncertainty that this is causing in your results.
Yeah, well, this answer that I gave you already shows you that probably the diffuse model is a source of systematic uncertainties, okay? There are others, of course. What we are planning to do, at least to assess this difference, is to use different models, different diffuse models, and see the results we have. We are not planning on creating diffusing models, diffuse emission models, not something that we are interested in doing, but we can use models from older versions of the models. We can use, I saw some paper, I'm not sure if it was that Malishev paper that I mentioned, but they try models like continuous emission on space for the galactic model, in which they only changed the normalization. We could use older models from previous versions of the catalog. We could, I saw some paper that tried to model based on gas emissions from the galactic center to create a model there. So we can use these very different models, see the results we obtain with which one of them, and then we can have some estimates of the systematic uncertainties, and we can use that in our results, for instance, in the SED. Because since the SED result is a strong result, it is important for us to be pretty sure about the results. So I think we should do this.
I agree. I think if you want to claim that there is a hadronic SED, you would need to do that work. Fortunately,
especially sorry to interrupt. Especially because the emission from the, as I mentioned to Regina, the emission from the diffuse emission is mostly hadronic. So it is important to take out this as best as we can.
I think that especially with dark matter studies of the galactic center, they've done a lot of this work for you already. And so if you look at the Eric Charles developed tools for Fermi Pi and the dark matter catalog that you could use if you would like to follow this up and do a short paper.
Sure. I talked to him in some Fermi symposium before, but only briefly. Yeah, maybe for sure it would be important to consider this kind of models for sure.
Okay, so just another comment, not a question, but I think it's very good that in your thesis and this work you analyze the spatial extension at different energies, because of course in different models that people have, theorists always come up with models, but there are some physically motivated models that lead to a different energy dependent extension. So it's very nice that you did this extra step of checking that.
Thank you.
And then I had a question about table 3.1 where you showed the fluxes. You know, this is very detailed.
I think it's great. I think I have also the slides with the table. It's the table that I showed in the presentation, right?
It was more a conceptual question, though. Yes. Mm-hmm.
Okay.
So there, your errors for the photon flux and for the energy flux for the two lowest energy bins are essentially the same, right, for photon flux, and for energy flux, of course, it decreases. And I was very surprised to see that, because I would have thought that at the lower energy where there are less photons and a lower TS, that the error would be larger. Now, proportionally, yeah.
Well, I never thought about that. There is one important thing to mention here is that we are quoting here only the statistical uncertainties that we obtained with the Fermi tools. We made an assessment of the systematic uncertainties here, but well, not here for the light curves, but since we are talking about flux here, we could use what we learned there. But here we are quoting just the statistical uncertainties. Okay. But yeah, I never thought about this, but it seems to be the error seems to be too small, right? That is the conclusion you are getting, right?
It's possible, and I think the systematic error for that lowest energy bin should be around 10%, somewhere between 5 and 10%, and you can calculate it from the effective area systematics, and see that may raise the uncertainty, and to me that would make sense. And then I guess my last question was, you literally wrote a book about the Fermi, what Fermi can understand about the galactic center. Is there anything more that Fermi can tell us about the galactic center, in your opinion, or have we, you know, with all of this data from Fermi, have we sort of gotten what we can from this mission?
I think we are very close to the limit of Fermi. I think we are. I think now we depend on other missions. I think we are very close. Unless, well, we probably learned something that with this work about the SED, but I think it probably, I mean, I'm talking only about the galactic central source. I'm not talking about other things. For instance, the emission from dark matter, or I'm not talking about it. I'm talking specifically about this source. I think we are close to the limits, yes. If we talk about other things like the diffusion emission, the galactic center excess, I think Fermi maybe can but this is a little outside of my specialty. But I think Fermi maybe can help still a little.
Thank you, Fabio. It was a pleasure to read this thesis.
Thank you very much.
Thank you very much, Jack. Thank you very much for your questions. And now, moving on, I would like to ask Professor Aion Viana to contribute with his start his questions, interacting with the candidate. Aion, please.
Yes, thank you very much, and thank you, Fabio, for this very nice presentation, and Rodrigo for inviting me to be in this committee. It's a real pleasure to listen to you and have read your thesis. The presentation was very clear. It clarified some of the questions I had, and it was also very nice to read your thesis. The thesis I found was really well written. The English was quite fluent and very nice, and that's not that obvious task to actually write a thesis in a foreign language, and it's a tremendous job what you did. So,
thank you very much. Thank you.
I'm very interested in this topic. I work with a little bit higher energies. As you know, I've worked a lot with Hess and now with CTA, but I'm not a Fermi expert, and I have a lot of questions about how the analysis is done and these things. I will not bother you with all my small little questions, but I do have some questions. This work on the galactic center is like, as Regina and Jack mentioned, is extremely complex. It's a notoriously complex region to do the analysis. I think the Fermi collaboration itself took a long time to publish anything on the galactic center, especially because it was so hard to actually give solid results in the galactic center. And it's an amazing job what you did. You got quite good results on it. I'm also interested, like Jack, in the systematics that comes. I think that's my main question, and I'll try to see with you what exactly can be done there. It's about systematics coming from this modeling of the diffuse emission, right? Like you show the residuals that you do have a lot of positive and negative excesses. Now, one first question that I have, it's a general question because I don't know how this diffuse emission is done, but I do know about two very important emissions. One is the Fermi bubbles, and the other one is this Fermi GV excess, and there's a lot of discussion in the literature whether the Fermi bubble has this, in the beginning the Fermi bubble had this flat emission, and now we don't really know if the Fermi bubble is completely flat, if the constant flux. Are these two sources modeled in the diffuse emission, and did you include these sources in your model?
The Fermi bubbles are included in the diffuse emission model, but well, since we used very large region because of Fermi limitations, we have to consider that. They are modeled and they were taken into consideration. The excess is not, but the excess is way fainter than the bubble. Okay, so the excess is not, but we didn't include any additional model to consider the axis. Okay, we just consider the galactic diffuse emission model.
Okay, and this diffuse.
Sorry. Just let me add one thing that I started and didn't finish. The bubbles, of course, very close to the galactic center. The bubbles are not modeled. Okay, they are modeled. I don't remember at which how many degrees away from the center, but very close to the center. They are not modeled, but there are still no confirmation if they get close to the center or not, and if their basis is at the position of Sagittarius A star or not. So, but they are not part for the inner degrees of the galaxy. They are not part of the models, but they are part of the models of the diffuse emission.
Okay, can you show the plot with the residuals so that we can?
Sure.
Because there are two trends that are quite suspicious. One trend is this trend that you try to. One first trend that I find slightly suspicious is this trend of the position that changes. So this is the residual, right? So so here we can see that there is emission, right? That it's not modeled at high latitudes. And the other thing is that apparently you do see in your positions that you have for lower energies, it goes to higher latitudes in galactic. It actually grows towards the north, right? The position when you do the position fitting, right? The position caused exactly because you have a mismodel emission in high latitudes, for example, like the Fermi bubbles or something like that. That you mismodel that and then it goes to higher latitude.
We were actually suspecting of a source, for instance, a point source close to the galactic center could also be becoming more and more relevant in lower energies. For instance, if we have a source that is very close, but peaks in lower energy than our source, and when we do this analysis, it's quite possible that this source was pulling the position of the source in lower energies to closer to it. I think that this is similar to what you are.
Exactly. Because if you have a low energies, you have a broad PSF, right? So even it's around 10 degrees, if I'm not mistaken. So even if you have sources which are located in the whole 5 degrees, 10 degrees, if you have a very intense source now in galactic latitudes, these sources will, like you said, might pull the position of the centroid of your emission, right, to higher latitudes or something.
Sure. Right? But talking specifically about the diffuse, this mismodeling, I'm going to call it mismodeling, okay? Talking specifically about it, I didn't add the residuals map, not even in the thesis, I think, but as I mentioned in response to Jack, we prepared models from scratch that did not have this modeling so apparent in these 3 different energy bands, and the position of the source were coincident with the position that we are reporting here. Okay, so the impact it's not that great. Okay, they were coincident within 1 sigma. So I'm not sure if I agree with you that mismodeling would create some kind of trends, could create some kind of trend in the position of the source for sure. But I don't think it created because it didn't show this trend. The same trend that we are reported was showing when we were using the different models. Okay, the ones that did not have this modeling problems. But I didn't add these images. I'll see if I have them. I think I didn't add these models to the thesis.
Yeah, because there is one thing that Jack mentioned, and I think you're very right that one thing that needs to be done is the systematics checks on different diffuse models. And it's in these models that were produced for the GVXS, not just the dark matter, but there are some results coming from there. And one of the most important, I find, and this is more of a comment for, is that these diffuse models, for the Fermi diffuse models, they normally neglect the injection of cosmic rays, recent injection of cosmic rays in the galactic center. The current injection of cosmic rays in the galactic center, it's almost zero for these broad diffuse emission models, which come from Gauss and things like that. And this is most likely false. We do see cosmic rays propagating in this region, and the HESS results, for instance, is one of these results that show that we do have cosmic rays propagating currently in the galactic center. And so this is something that, for example, this emission that you see, definitely there is more emission in the center than the diffuse emission, the normal Fermi diffuse model is measuring. So, and this trend where you see very deep negative excesses, do you understand them? Like, why do you have very negative and very positive excesses? Do you know why this happens normally?
Are you asking specifically about?
Yeah, I'm asking about. Yeah, about this MEV and 3GG.
Well, since here, for instance, I think I can give you examples. Some of this excess, yes, I would say the answer is yes. Some of this excess, I would say the answer is no. We don't know the reason. For instance, this bands of mismodeling here, for sure, the origin is from the galactic diffuse emission. It can be for two reasons, either because the galactic diffuse emission has its imperfections, and also because we didn't model it very well, which is probably the reason for this case, because this was created with that minimal modeling, minimal fitting that I mentioned. Other mismodeling, we don't know the reason. I can show you, for instance, I think you can see that I'm pointing here, right? Mm-hmm. There is this green arrow, this green cross here, or here, or here. These are all point sources that we included in the analysis. And this is something that is usual to do in Fermi analysis. You find there an excess, and this excess is in a region. It can be for several reasons. We don't know the reason, but what we try to do is to include a point source there. So this excess that is can be explained with a single with a point source. We just say it. Okay, I'll include a point source here, and this excess is taken care. Okay, it can be a new source that is really there. Sure, it can be. But it can be only a mismodeling or some problem with the diffuse emission model. It can be for several reasons. So some of them we know, some of them we don't. For another example of excess that we can understand and we know the reason is, for instance, if we have a source that was not flaring when the catalog was created, but it flared very brightly after that. It's going to show as an excess there. But we know that this excess is because of the behavior of some specific source that was flaring and we were not considering. And then we just model that region again. We free its parameters, and it is taken care. Of course, not perfectly, because it wasn't flaring. For instance, here I show you in these plots, I'm showing you the 11 years of observation. But if it flared for a few days or weeks, it is not perfect. I'm going to take care of this flaring for that period. But, you know, I'm going to show here the average. residuals. Okay?
Definitely these negative excesses, most likely they come from an overfitting of the diffuser. You're fitting too much because there is emission that is not modeled. So the diffuse emission eat up those sources, and it eats some emission which is not supposed to eat, and then you have negative residuals there, which are very strong. So clearly there is a necessity to actually model that, and yeah, but that's good, and especially at low energies.
So you mentioned, if I may, so you mentioned something that made me curious. So you mentioned that the diffuse emission should take into account recent injection of cosmic rays. What did you say exactly?
Yes, if you look at how the Fermi diffuse emission model is done, and then you take into account and you look at what is the cosmic ray, the recent source injection of cosmic ray that is taken in these models at the location of the galactic center, is very close to zero, if not zero in most of the cases. So it completely neglects the fact that the galactic center is actually the place where in this small region you have around 5% of the star formation of the galaxy, and we saw in Hess that we do have cosmic rays propagating there. So these kind of emissions, they have to be added necessarily to these models. In these discussions on the Fermi GeV excess, I think there were a couple of papers. I think Tim Linden is one of the persons who actually took this into account, where he actually corrects the cosmic ray, recent injection of cosmic rays in the galactic center, and he sees that he can actually model a lot of the Fermi GeV excess with it. And as a result, you also get a component which doesn't look like a dark matter anymore, but it looks like a bipolar emission, and
I saw
the Fermi bubbles.
Yeah.
So this kind of emission, we have the central molecular zone in this region, right? In this whole region here, we have a lot of molecular clouds, and if you have cosmic rays there in this region, not just the sea of cosmic rays, recent cosmic rays propagating there, we do expect more emission coming from this region, and this should be true. This is one of the things that we are discussing currently in CTA, is how to model these kind of emissions close to the center, to the galactic center. So the other question I had is how, could you explain, I'm not sure if you did during the presentation, I apologize, but how exactly did you calculate the extension of the source and to come to the conclusion that it might be point-like or not? Can you explain that?
Sure. I just mentioned briefly during the presentation. Maybe I have, well, I may have some slide about it, but okay. We used FermiPy for this kind of analysis, and FermiPy has a method that is called extension, and the same method also finds the position of the source and things like this. For the first, this method finds the best position for the source. Okay, so it takes the current position of the source, and it creates it checks the TS map around the source, finds a maximum, creates a square around this maximum, and then tries to find the maximum in the likelihood function in this little area of the sky, and then it finds the position. To find the extension, what it tries, what it makes is to you can give any kind of model for the extension. We used 2D Gaussian, but you can use a disk or whatever. You can even propose some formats for the extension if you are observing some source that is extended in some different way in other wavelengths. You can try to use it, but what we used was 2D Gaussian, and then it starts to fit this to the Gaussian with different radii to the same emission, and it calculates the TS for every try. So after that, it gives us, okay, the best value for your extension is this, and the TS for extension, is extended versus point source. The TS for extension is this. If the value for the TS for extension is too low, we disregard the extension. If it is too high, we have some indicative that the source is extended. This is how the method works. But given the large amount of source in the galactic center, the diffuse emission, and all of that, we could not use this method completely, because we started to get very strange results in terms of TS with values like extremely high or extremely low, like things really strange started to happen. So instead of that, what we did is that we considered we had the value of the extension. We disregarded the very strange ones. So we considered the values of extension when the method worked more or less well, but we were not very sure about this result. So what we did is to say if the source was point-like or not point-like, so to have some kind of confidence in the results, we compared the upper limits that we obtained with the uncertainties in the point-like position of the source in the catalogs. So I'll give just one example, but it is the same, only with different catalogs. For instance, in the low energy bands, we had that uncertainty, that upper limit of 0.24 degree for the source. So we went to the catalog of low energy sources, Fermi low energy sources, and we checked every source. We saw the uncertainties of every source there, and we got an average value for the uncertainties of the point source position in this catalog. And the value was very close to 0.24. I think it was 0.25 degrees. So the uncertainty of a point source in the low energy catalog was larger than the upper limits that we were not very confident in, but was larger than the upper limits that we obtained for an extended source. So we decided, okay, if it is considered a point source, even with an uncertainty for a point source larger than the upper limits that we are obtaining, we can consider that this is explained as a point source. Okay, so this is how we did. We could not use totally the Fermi pi method, unfortunately, but the results we obtained were similar to point sources in other catalogs.
Yeah, I thank you, but I just don't quite understand, why do you compare the, in order to compare, to see if your angular size is point-like, you compare to the position uncertainty. The position uncertainty is why don't you compare with the actual angular size of known source, like AGNs, which are known point-like sources, and you compare the size to AGN sizes? I don't understand the positions.
Okay. Well, the answer to this is that this is the method that we chose. Maybe we could have made this like you're suggesting now. For this low energy catalog, we don't have the angular size. Okay, they are point-like, and that's it. I would have to find this value. I'm not sure if they are available, at least not a large number of sources with angular sizes. Of course, for the extended ones, yes. But if it is point-like, I don't know if we could find this information. I'm not sure. I would have to check that.
Right. Okay. That's all right.
What we try to do, just to make sure, is that if the results we got was like incompatible with results for other sources. So we decided, okay, if I'm unsure if this source is in this position or in this other position, maybe no. If it was modeled as extended, it would probably cover the uncertainty of the point source, and even more than the uncertainty of the position of the source, the point source. And if our extension upper limit was smaller than that, okay, so it is probably not extended. That is the conclusion that we got. But actually, we did not use very much the information about the extension. We use mostly to be able to say that several other sources are close or coincident with the source. Several other potential sources other than Sagittarius A should be considered. That's the only reason that we use the upper limits.
Okay, thank you. Yeah, because I'm asking this because I was wondering, you mentioned on your in slide 34 about the if it could be dark matter. Dark matter is another topic that I'm very fond of. So I was wondering if the kind of upper limits that you get on your angular size, because you see the dark matter profile, like it is expected to be peaky. You do have
yes.
And some profiles are extremely peaky. They do have and I was wondering if the kind of upper limit that you have can actually rule out the dark matter. Of course, the extension of dark matter, it's extended and you could see a much wider, but around the point-like source, you do expect perhaps to see some kind of extension or a small peak, right? Something that it's very like source, but it's slightly more extended.
I agree with you. I agree. The models that try, for instance, what people try to do a lot is to explain the galactic center gamma ray excess with dark matter, and this is, of course, much more extended than a point source, for sure. Of course, you know that. These models that consider point emission from dark matter, the first I'm going to be honest with you, the first paper that I read considering this kind of emission in gamma rays, okay? Of course, I know the models for dark matter, the point, things like this, but the first one that considered maybe the emission of gamma rays from dark matter annihilation can be pointy or like pointy-like or things like this. The first paper I read about it was later when the thesis was finished. So I didn't consider it. But when I read it, I thought to myself, maybe we should consider this kind of thing. I think you're correct. I mean,
there are some quite exotic models where you have a diabetic compression around the black hole, and you have and stuff like.
But I didn't know this
source with dark matter.
I was mostly based here on there is a paper from the Fermi collaboration that it is about the emission, the gamma ray emission from the central part of the galaxy, and there they consider the dark matter, and they always talk about it, this emission, about it being extended, and this is what motivated us to consider this candidate. But yeah, I also read some different models from dark matter that could not be ruled out only on this argument. You are correct, but it was later when the thesis was done. But yeah, sure. We didn't test this, okay? Just to make sure.
Okay.
We didn't test this.
What about the question of being leptonic or hadronic? You say at the end, you conclude that it's most likely hadronic. Are you sure of that? Like, are there any other leptonic models that
I'm not sure about that. We think that the results that we obtained are more compatible with hadronic emission, especially the SED. Okay, of course it could be. I mean, the SED is pretty similar in shape with the SED of the hadronic models. And a hadronic model is expected, or acceleration of protons is expected from Sagittarius A star because it is a RIAF, and it is something that you expect in RIAFs. But of course, we are not sure about that. But it seems more likely based on the results that we got.
Yeah, but for example, there are some models you show in your thesis that the pulsar nebulae, which is located very close to Sagittarius A star, of course, the past models of these PON they don't fit, right? But they don't fit because they were not trying to fit the Fermi.
Sure.
But for example, there are models nowadays with leptonic scenarios from Sagittarius A star that can explain. I think you showed in slide 25. There is at least one model which is purely leptonic, I think, that can explain that. 2025. I can't hear you. I think you muted your microphone. Fabio?
You are muted, Fabio.
Oh, sorry. This is the slide, right? Sorry.
Well, this is my basically
the only pure leptonic model is this one, okay, right. From Kuzonosi. This other one is the same model, but they were trying to fit. I'm not sure if it was magic data, or they were trying to fit some TV emission with the same model. We can disregard this one because they say that this one is not a good model. This one, they were using Malishev's data. No, not Malishev, but Chernyakova data. Is the only pure leptonic model. This other blue one here is the leptonic component of the hybrid model of GUO 2012. But I don't think and you are saying that they both of them don't be compatible with our results, but you're correct, they were created with Malishev's data that is quite different from ours because it continues here, and we consider that this is probably because of contamination from the galactic diffuse emission in their models, because they were working with models from a few years ago that were not updated. So we are working with better galactic diffuse emission models. But yeah, okay.
Yeah, and of course, like you said, if you confirm this bump here, this is a very clear, almost smoking gun signature for hadronic emission, the pion bump.
Sure, but sorry, go ahead.
Yeah, but of course, you have to confirm it, right? Like you said, there's a lot of systematic checks that need to be done, and I think one future task is actually to try to write the proper band of systematical uncertainty that you have, not on the
sure.
Around the SED, right? And you do expect to have a higher systematical uncertainty around these. Of course, if you can show that you have a pion bump there, that's a great result. That's a huge smoking gun for the emission mechanism of the central gamma ray source. That's amazing. But I think that's much more to be done there. So my final question is looking at the future. Like in this sense, if you come to the conclusion that the systematical uncertainties of Fermi are too large at these energies, they might be, and you can't really show that you have a pion bump. How can you actually show that it is with the, let's say with CTA, let's say, how could you show that it's hadronic and not leptonic if you can't really disentangle sources of energies? Is there another way to disentangle?
Well, I don't think that since the bump that we are showing here is, we would have to use energies below CTA limit. I don't think we could use CTA for that. When I said about using CTA to check the hadronic origin of the emission, I was talking about the TV emission. Maybe I didn't make it very clear, but I was talking about it. So I was considering the gamma ray as a whole. For the gamma ray TV emission, I think CTA will help. Will also help to find the position where the TV emission is coming from, and maybe make maybe find, oh, it's coming from this region, and this region is very rich in gas and things like this. If now talking about the low energy part of our SED, I think we would have to count on some data from Amigo and eAstrogram and
yeah, even without the low energy part, the high energy part, do you think you could disentangle the source? You could see if it's leptonic or hadronic?
Okay, I'm talking here about a two sources scenario, like one population, which is considered in almost every hadronic model that I showed you in that previous plot. They always consider two populations of protons, one that is responsible from the TeV emission, and another one from the GeV emission. And for the GeV emission, I don't think we could use CTA. But for the TV, for sure, we could get an SED with better results that could help us at least fit models better. And there is this association with regions with gas that CTA could help. But for the components that is emitting in GeVs, I don't think CTA would help a lot, because it would be measuring the SED in energies after the bump. So I don't think we would be able to make this to use CTA data in these energy bands. That's
all right.
The same that we are using here.
Okay, thanks a lot. Yeah, I will stop here. I have lots of questions. I could go on and on, but I will ask these questions in another moment.
Yeah,
we'll have opportunities to actually discuss this study, these works.
You can send me an email and we can continue the discussion.
Of course. Thank you very much, Fabio.
Thank you.
Thank you very much, Aion, for your questions and comments. And now we will follow up with Professor Gastao. So Gastao, please.
Hi, thanks. I'd like to start thanking Fabio and Rodrigo for inviting me here to this defense. Even though I work with puny photons of X-rays, not these huge photons of gamma ray emissions. So I had a few questions, but there's a lot that was already asked and discussed. So risking to be a little bit repetitive, I'm going back to a few points. There's one thing that amazes me with gamma ray emission is the idea of point sources. The thing is that you have a very low spatial resolution compared to all other emission in the electromagnetic spectrum. So when you say, well, it's a point source, how big is it actually? I think you said 0.4 degrees sometime but
yeah, I'll show you. I think this will help to answer your question. Just a second up here. Maybe this.
yeah, that one. Yeah, that's good.
Yeah. Well, they are. First of all, there is one thing that is important to mention is that the PSF is large, and it is larger for lower energy photons.
Right.
So it changes. The size of a point source changes with energy. Okay. Here I'm showing you the same source in 4 different energy bands, and it is modeled as a point source in this energy band here, the green circle. It is a point source, so this is a huge one, like 0.06.
Sorry, Fabio.
Yes.
Sorry to interrupt you, but I think you discussed that with Aion, I think, and this red circle is the uncertainty that you have in the position, or is the size?
No, this is the uncertainty in the position. Yeah, okay. You're correct. You're correct. The 68% confidence level.
That's not the size.
It is not the size. You're right. We use it like an approximation to the size. You're right. But this is what you use. I mean, I don't know if I have here the size of the stars. I'm pretty sure I don't have it.
Well,
Gastao, can I pick back?
Sure.
Sorry for that.
My question. Yeah, sure. Go on.
Yes. So Fabio, because you're talking about the size of the PDA, the PSF, or the precision in the location of the center, because you can find the center with a much smaller size than the size of the PSF.
That was exactly what I'm going to say. I was thinking about Gaia, for instance. Gaia has some PSF when it observes the stars, but it has a very precise, it can locate very precisely the location of the emission. So that's why you have a nice astrometry. But you could not say so much about the size of the sources. So I think that's the same thing that's happening here.
Yes, it is. This is the uncertainty of the position of the center of the position of the source. It's not a measurement of the size of the source. We are not trying to measure the size. It only makes sense, I think, for us to talk about size when we are talking about the extended source. I have, if it was extended.
The figure 3.4 of the thesis has the upper limit on the angle.
This one, yes, this one. In this case, we are talking about extension, and then the source is huge. But we are only showing you the upper limits of this extension, the 95% confidence level upper limits. So,
okay, but that's okay. So if the source is, well, it depends on the energy. And if you go to higher energy, you can say, wow, it's smaller than 0.05 degrees.
Yes.
So it must be smaller than about 7 parsecs. So
yes.
That's what you can say. That's the only thing you can say about the size of the source.
About it, yeah.
It's punctual emission, right?
Yes. Yes, the size is here, but this is considering a model in which the source is extended. but actually the models in which the source is point-like are preferred.
Okay.
But we are showing here that well, there is all that things that I was answering to Aion about the way we used to measure if the source was or not, was point-like or not. Not only use the TS of the extension, because we had some strange results. So when we consider the extension upper limits here, we are only including it here just to say, look, the source is, if extended, is occupying a projected extension of almost 40 parsec, 35 parsec at the galactic center. And in this region, there are lots of other sources that could be responsible for the gamma ray emission.
I see.
That's the reason. But we don't try to argue for the extension. This is not what we are trying to do. Maybe the way we are showing the results is a little bit confusing. But that's the reason to quote the extension upper limits here.
Okay. Well, it's a little bit different from other wavelengths, the way it's done. Okay. So your best fit is a point-like source. Okay, that's the bottom line.
Yeah.
So if it's, but even so, so it's a point-like. So now I'm going to the question of the variability. So you say that the emission comes from somewhere near the supermassive black hole. It's related to the supermassive black hole. That is your hypothesis, right?
Yes, yes.
So, and you said a lot of times, and you wrote on your thesis, that it's observed, we observe variability in X-rays and the near infrared.
Yes.
But the period of variation, this periodicity, it's something of a few hours.
Yeah, sure.
So I think it would be hopeless to look for such a variability with the Fermi LAT data, right?
Yeah. Yes, to look for this everyday variability, for sure. There are a few flares in X-rays and infrared that are, for instance, there are flares in X-rays that are hundreds of times larger. The flux is hundreds of times larger than the quiescent flux, okay? So if you are correct, we could not expect to find some correlation of a gamma ray light curve with 15-day beams, for instance, with daily flares, for sure, except in the case of an exceptional bright flare. That are the ones that I included here, but if in which the flux were hundreds of times larger than the quiescent flux. But even for these ones, we couldn't find nothing. Other things that we tried to find, and it's not related to the flare would be great. So we could for sure associate the source with Sagittarius A star. But we also included some other things that we were looking for, and we could have found, if it was the case, are what we are calling orbital ephemerides. We are considering here two of them. This one is the pericenter of the G2 object. The G2 object is a cloud of gas that got very close to Sagittarius A star in this epoch. And here is the pericenter of the orbit of the S2 star that got very close also to Sagittarius A star in this period. And we were considering these two ephemeris, these two events could provide enough fuel to Sagittarius A star to exhibit higher emission, not only in gamma rays, but also in other wavelengths. And this could be could have a variability that would not be very short on time, like 15 days, like a few hours. It's something that the emission would show very clearly that it is higher than previous emission for an extended amount of time. But this also, we couldn't find this. It didn't happen. It didn't happen even in the other wavelengths.
Yes, and then I'm glad you are with this figure. In the other one, the previous one, but you have 1 or 2 points that's a little bit above your mean in 2018. There's one, but you say that it's this only
one,
upper
right?
limit. Yeah, that's this one.
This is an upper limit, yeah.
But it's there.
Yes, but when we consider, sure, you saw, I don't know if you remember, because it was many years ago, we were trying to, and it is the same thing that I was answering probably to Regina. We had in previous light curves, we had a few moments in time in which we could see some flaring, some potential flaring. And you remember, you probably remember, I don't know, that we tried to fit exponential functions there to measure the extension in time of the flare, and with that we could maybe get the size of the emitting region considering its light crossing time and things like this. We tried to do this very same method with every single point here that you are seeing that is above the average, and we couldn't, because the variability is random, and so from this, then a high energy flux, a high flux here, then a low and a high, so it's changing so rapidly in 15 days, but rapidly, that we couldn't do that. And also, I think I have here, maybe I can show some slides in which we consider these points with the average flux, and only like 1 or 2 is not coincident with the average flux, considering only 1 sigma. If we consider 2 sigma, every single point of this light curve is consistent with the average flux. So it is too little to consider it, of course, a flare. And more than that, we are here just quoting, although we estimated the systematic uncertainty for the light curve, we are here quoting only the statistical uncertainty, because since we were not finding flaring, even with the smaller error bars, if we increase these error bars, we would not see also. But the systematic errors were like 10 to 12% of the error. But anyway, they were, all of them consistent with the average flux. So not in 1 sigma, in 1 sigma.
Okay, so in other words, what you can say is that it's incredibly stable, the emission, within the period of, say, 15 days, a month, and a few years.
Yes.
Yes, and that's incredible. I mean, for a supermassive black hole, you would, I mean, I don't know if, I'm no specialist, but I would expect some more variation, more periods, things happening in there. Not really periodic, but things falling and increasing the emission.
Yes. Go ahead, sorry.
I would just say that when you see something so stable, I would associate the main mechanism to something that's stable also. And then I would think, as it was already said here, in the cusp of the dark matter around the center of the galaxy, or even a population of millisecond pulsars that are living there and emitting happily their gamma rays, but not with well, it's not an AGN, but a weak liner, perhaps, in the center of the galaxy.
Oh, it's much weaker than a liner.
Well, actually, it is much weaker than a liner.
Yeah, it is very weak source, and actually most of the supermassive black holes are in a quiescent state. Sagittarius A star, it is for sure. We can see this variability because we are very close to its other wavelength.
Perhaps may I add something, Fabio?
Sure.
I don't want to say much, but Gastão, if there was a blazer, if there was a supermassive black hole accreting at the levels that we see quasars and blazars, well, we would be using Sagittarius A star to guide our airplanes, and during the great Christopher Columbus and all the explorers, they will use Sagittarius A star to guide themselves to new undiscovered lands.
Okay.
The thing is that the Sagittarius A star, I can give you the number. The accretion rate of the black hole is about 1,000 times lower than a liner, actually. Yeah, it's about 1,000 times lower than a liner. Okay, 1,000 times. Okay, but the thing is that the emission processes many of the emission processes associated with the accretion disk, they don't scale linearly with the accretion rate.
Oh.
So if it is 1,000 times lower accretion rate, some processes will be 1,000,000 or 1,000,000,000 times weaker. Okay, so this is the reason why it's not. This is what I was excited when I proposed this project to Fabio. Maybe we can see some feeble variability when looking at the light curve in detail. I was hoping, as was discussed with some committee members, that perhaps we would see the counterparts of some of the X-rays and near infrared flares in gamma rays, but unfortunately we didn't see them, even after the exhaustive analysis that Fabio performed.
Yeah. Okay. So I have one question. It's a very minor question. Let me just find where I put that. It's on a table. It's when you are saying that there's no trend on the light curve.
Okay. I have this table here.
Yeah. Where did I?
No, it's not this one. Just a second.
It's your thesis is. Yes.
I know.
3.4 on your. No, it's not that one.
Is this one?
It's not that one, but let me see if there's.
Yes, this one is for all these other light curves.
It's on the PDF. One. It's table 3.4.
Yeah, I think I didn't include this one here in this slide. Sorry.
No, because I had a doubt with the numbers.
One of the numbers, I think in this table, there is a typo in one of them. I found this. I will correct before I...
okay, because looking at the numbers, it seems that, well, there's a typo because the linear coefficient on flux, photon flux is compatible with 0, and clearly it's not looking at...
Yes, that's the typo, yeah. One of them is like 2 orders of magnitude wrong.
Okay.
1 or 2. I found this typo when I was revising the thesis. Yeah.
Okay. Just to be sure that I was not dreaming something.
No, you're correct.
No, I have just a curiosity. It's about the Fermi satellite.
Mm-hmm.
It's been around for what? More than 10 years.
12 years.
It's still working. And what's its life expectative? No, life
expectation. I don't know. Yeah, I understand your question. I don't remember the exact number.
I mean, from now, because I think it's already over-aged. It's initial.
It is over-aged. I don't know the life expectation.
How long do you expect it to be functioning?
Well, a few years ago, it had a few problems, and the mission was in jeopardy because of this. But they managed to solve the problem. I don't remember exactly what the problem was. I think it was something to do with the solar. I don't remember. They had to change the way Fermi was orbiting. I don't have.
No, I mean you, the community. I mean the the people.
At that time was when I was actually there in one Fermi symposium, and people were not, at least in the discussions that I saw and I took part, people were not trying to make bold assumptions about how long the Fermi would continue working, because it was actually in a very bad state at that time. It was solved, but I don't know. I don't know. Maybe Jack, Regina and Jack knows.
I think Regina wrote something.
Yes, I didn't want to jump in, but I can say a few words because I think this is a bit out of the context of what you'd be expected to know for your thesis.
Wow, it's
yeah. Well, I mean, so the issue that Fabio, I mean, he well described. There was an issue with the solar panel, and so what happened was actually, so the solar panel is on a gimbal, which allows it to tilt back and forth to observe the sun. And what happened was it got stuck. And the fortunate thing was that it got stuck at a good angle. And so they tried a few ways to adjust it, but it was never able, it just stopped moving. But because it was stopped at a good angle, we don't actually have to, like, it's okay. We can still have power for the instrument. There isn't an issue. There is a question of, does that affect the other solar array? And, we just don't know. Like, the original lifetime was 5 years and we're now at 12 years. So, things wear out. But as far as the instrument goes, it's not, I mean, it's degrading in a very predictable way, and it's degrading very slowly. There aren't any consumables on board, so we won't run out of anything like fuel or coolant or anything like that. The orbit is predicted to decay in 2045. So that's quite a ways away. And so, right now, all the, knock on wood, the instrument is performing well, and everything is going okay. So,
okay.
There isn't really a predicted end of life.
Okay, I asked that for two reasons. First, because we're talking about satellites, and I thought about XMM Newton and Chandra, who had also I think 4 or 5 years for the nominal mission, and they are working for 20 years now. So it's not bad. And even XMM had some doubt in the past, I think 10 years ago, because there was a matter of stopping paying for it, and people were talking about switching it off. But then they found the money, and it's working, and we're happy. And although it was hit by micrometeoroids, so it lost a few CCDs, but it's working. So it's good for XMM and better for Chandra. And the other reason was that, I believe that if you continue monitoring the galactic center, you will go, it will be better for your statistics and for the systematics that you discussed also. And that, I don't know, if it goes to 2045, is that for the next 20 years, that will be great. So that was the two reasons I asked about that. So I'd like to thank you again, Fabio, for your very nice presentation and for the thesis that you wrote. As Aion said, it's very well written. There's a few typos, but
yeah, I found some. But
in a 270 odd pages, which, by the way, is huge for our standards. It's a very big thesis. Really, it was enjoyable to read, and I learned a lot on. I've been following Fabio's work for the last 4 years because of our postgraduate rules at USP. So I've learned a lot in this like 4 years about Fermi and gamma ray astrophysics. So thank you again, and well, good luck with the future and continuation.
Thank you very much. Thank you. Thank you.
Thank you very much, Gastão, and thank you for being the relator of Fabio over the last 4 years. For those that did not know the process, so in our department, every graduate, we pair each graduate student with one of the faculty, which is not the supervisor, and so this faculty acts as supervises also the progress of the students. So Gastão was the supervisor that was in charge of Fabio. So thank you, Gastão. Very good, and we hope that Fermi continues getting funding until 2045. We hope there will be another neutrino emitting blazar that will bump up funding and gravitational waves and merging neutron stars and stuff like that. Very nice. Okay, so thank you again, Gastão. So now let's move on to the last committee member, Professor Eduardo Cypriano. Edu, please, you may begin.
Thank you, Rodrigo. Thank you for inviting me. Thank you, Fabio, as well. So, as well as Gastão, I had the opportunity to be in touch with your work like a couple of years ago, during your qualify. I remember you were my grad student, Astrogalactic. And if I'm not mistaken, you were my undergrad student as well, haven't you?
Yes.
In the data analysis course,
yes.
Wasn't it? Great.
Yeah.
Because what I'm going to ask about.
Yes, I know. I was dreading this moment.
Fabio, are you the first former undergrad in astronomy that finished the PhD with us?
I think I'm not. I don't know. The PhD, it is possible because I didn't took a master's degree before. I went straight to PhD. So it is possible. I'm not sure.
Oh, I think you are actually.
I'll ask around, but
well, thanks for pointing it out, Eduardo.
It's huge. It's huge. It's
wow. Yeah.
It's a very proud moment
for the
department. Okay. So, so if Gastão complaining about his puny photons, I'm lost for words because I'm an optical astronomer, and well, there's a lot of optical people watching probably this defense on YouTube. So let's get clear of the first question, which which was because in the 80s and 90s we make fun of X-ray astronomers because they couldn't name their photons because they are so few. Wow, they make progress, but now we have gamma ray photons. So how many photons are in all your thesis?
Yeah, well, I knew you were going to ask this question. I didn't get the exact number because my computer at the university is off for some reason, but it's something in the 100,000 order, like 100,000 photons or things like this.
I know that's a curiosity, but it is tells how difficult is the work you have been doing all these years, because there's so few photons if you compare with any other area of astronomy, and we are talking about 11 years of data, that it tells how hard is this work. So congratulations again. So you said that in a second, a lamp have much more photons than that.
Sure. Yes, we were talking about it before. In a lamp that is on in your room, it is emitting much more photons in a second than Fermi has collected in all these years, in much less than a second. Yeah.
Impressive. Okay. So let me start asking about the So the time series, so you try to detect some variability in the data. So if I understood well, you put all your data on those histograms, did Gaussianity tests, they come up with a consistent with Gaussian, and therefore you said the process is random. Is that how you proceeded?
Well, yes, you make it look like it was a poor analysis, but yes, actually, what we if you look at the light curve, you don't even have to make a lot. For instance, this one that I'm showing you with the average flux and the 1 sigma uncertainty of the average flux, you can say that there is no variability in this light curve, right? I mean, unless there is some region with a single point that is a flare or things like
so,
that.
But that's not the point. Is the analysis procedure, because when you do that, you not using the whole information, because you know that one photon arrived after the other or one beam. So there's a time series, there's a sequential data.
Sure, okay.
So for instance, I could build a Gaussian distribution of points, and I could put all the data points which are less than the average in the beginning of the time series, all the ones with positive put in the end,
sure,
and I will have some step function. So,
yeah.
So the procedure you are doing, so you are right, the overall distribution are consistent with Gaussians. You did very old school P tests, and you proved that it's right, but it doesn't mean there is not a variation. So
yes.
for instance, I think I can see something in the 180 days. And in the course we did undergrad, we learned about this run test. We check whether there are a sequence of positive or negative residuals. And there is what to expect if the process is random and what to expect if it's not random. I'm pretty sure that if you do these run tests in this data I'm seeing here in the screen, that will give an answer that this is completely random. So this is a test that tells about how random the data is, considering this a time series. And in the 180 data, I think, well, I don't have the data, but I think we can see some correlations in the residuals. There's some 3-4 points that are.
I'll show this plot just so everybody can see. Just a second. Keep on.
Yeah, so it's that. So it might be a low significance because you don't have a lot of 180 beams, days beams, but so there's another one that's the one with. So let's see which page of.
I think that is this one. You can see which is like some waves, right? Is that
just a second? I mark here. So let's see, because I was looking to the thesis. So yeah, that's the one. So maybe if you do a runs test or some other tests, you might see that there's something there, which is not completely
okay.
devoid of significance.
Yeah, I'm sorry. Can I go? Or?
Yes, you may go.
Okay. There is a few things that you mentioned that I would like to comment. First of all, yes, I remember the test that you mentioned now. I'll probably make it in the next few days just to make sure. If I'm not mistaken, I have some code that I used during the course to do this. It's probably going to be very hard to find it. Probably easier to write again, but okay. The second thing is that we just did, the only test we did was not that distribution. As I said, we first compared with the average flux and things like this. And after that, we also checked for some global trend in the data. So if it was something like the example that you gave very correctly, that maybe if I order the fluxes in time, it would still be a Gaussian, but I could see that it was rising or lowering, I don't know. But we did some tests to find this kind of thing. But you're correct, there are other tests that we could do. Now, specifically about this light curve that you are seeing, this one is in the 10 to 500 gigaelectron volts. For this reason, it has a larger time beams because we could not get statistics with smaller beams because we are talking about very few photons here. And we were not trying to find variability in this light curves, although maybe here it seems to be something, but the number of time beams is so low that it might be a coincidence also. So what we were trying to do with these light curves was some other analysis, trying to find correlation in energy bands, in different energy bands. But we knew we wouldn't find because we couldn't see that there was nothing to correlate between these light curves. But I included in the thesis for the sake of completeness. So I would show you, okay, we did this. We couldn't find anything, but it might be interesting to do that test, run test, right? I don't remember the name of the test.
Yes, well, that's one that. Well, we have a lot of people that do variable stars in our department. They know a lot of statistical tests on sequential or time series data.
If I may add, Fabio, didn't we do a sliding window tests on this time series? I forget.
I think we did, but many years ago, I didn't include this analysis in the thesis. It was on that light curves done with the previous catalog.
And I'm pretty sure we did a Fourier transform.
Yes, we did.
There was nothing, if you are referring to that, nothing shows up in the Fourier transform. So.
I did for including the light curves in the thesis. I don't know why I didn't mention it. Mm-hmm. For this light curve, I didn't do the Fourier analysis because it is so short. But with the 15 days beams light curve, I did, and there was nothing there. Yeah, I should have included that.
Okay, thank you. So another question about the SED.
Yeah,
there's a phrase on the thesis, like we created a total of 7 SEDs with different selection of free parameters.
Mm-hmm.
I don't think I got it. So you have completely different models. So the functional forms are different for those 7 SEDs, or it's just like you change parameters and then you have the 7.
Okay, I'll explain that.
Because if it's the later, then you my follow-up question would be why you simply fit all those parameters with the data and got the best answers.
Okay, when we are using the Fermi pi method SED to make the SEDs, we have some choices that we can. The first thing is this SED depends on the model, the way we are modeling the gamma rays that are being detected by Fermi, attributing it to different sources close to the source that we are analyzing. Okay. Roughly, this is what we are doing. When we do the SED, we can leave parameters from the nearby sources also free. So maybe if I think that some other source is too close and too bright, and could be impacting the result that we are going to obtain with our SED, I can let this other source free during the SED creation. And we selected the closest sources, sources from the Fermi catalog, the closest ones and the brightest ones. It was a list of, I don't know, maybe 5 sources. I don't remember the exact number. And we tried different combinations of 3 parameters. If I'm not mistaken, only the normalization of the sources, but maybe some index also, I'm not sure. I don't remember now. It is in the thesis. And we let this free, and we tried several different SEDs. All of them show this same format, the same bump. And we used that archaic method to select the model that better explain the data with fewer free parameters. And the one that better explained the data, the one that explained the data with fewer parameters, there is a relation between this was this one that we are showing here.
Thank you. So that makes a cue for another question. That's I was a bit surprised that a thesis with so much data analysis didn't mention the word prior or Bayesian analysis, not a single time. The only mention of Bayesian is on the references. And for instance, all you said about fixing some parameters on the foreground, population, other things, you could put everything in the same model, but using some priors on those models, on those parameters. So you use maximum likelihood all the time. I don't know if it's a characteristic of the area, but I'm pretty sure that some parameters you have some information come from model or from other data sets that you could use to further constrain and improve your modeling. Isn't it the case?
I'm not sure. I don't know. Well, what you said is true. I'm not sure if I understand 100% what you are asking, but I don't.
Yeah, are you asking, Edu, about the applicability of Bayesian statistics to the work?
Basically, well, he just mentioned that he made some options on the SEDs regarding, for instance, like fixing some parameters in one case, letting it loose in others. But we could do this together if you can. Well, if you have any reason to fix a parameter in something, it's probably coming from a prior knowledge, coming from data or from the physics of the source of something like that. And if you do a Bayesian modeling, you can make it more organic. You can put everything. You don't need to do like several models. It can be just one model with priors.
Okay, there are two things that I would like to add. The first is that we selected which parameters we are going to let free or not based on some prior knowledge that we had about the sources. We did the same thing. I think it's better to explain. We did the same thing to decide which parameters were going to be free in the light curves based on variability of the other source and things like this. So there were some prior acknowledgement that we used to select which were going to be free or not. The second thing is that we have a limit on the number of free parameters in this model that we are using. There is about 15. There is not, it's not written in stone or things like this, but the documentation of the optimizers that we used to get to to maximize the likelihood indicates that we should use fewer than 15 parameters. So we had also this constraint, so we could not start freeing every parameter that we had some reason to make maybe let free. We had these limitations, so we try to combine in different analyses to get to a result. I think I don't remember quite well how the parameters were chosen to be free, but I think that always the same sources were, or more or less the same source. As I mentioned, there were 5 or 6 sources, plus the diffuse galactic diffuse emission and the tropic diffuse emission, and the source of interest, of course. So a total of about 10 sources. And what I changed between these 7 analyses that you mentioned was, okay, in this analysis, I'm going to let, for instance, the normalization free for all the sources. In this analysis, I'm going to let the normalizations free and the index of this source and things like this. That's one constraint that we also had on selecting. And I think that's all.
So, Fabio, I'm pretty satisfied with your answer. We can talk about this later, but I'm just saying, when you fix a parameter with a given value, it's like using a prior function, which is a delta of Dirac. You have infinite knowledge about this parameter. When you do it you can do like a Gaussian function, because it can take into consideration some uncertainties. So then the parameter is not completely free, but is also not 100% fixed.
Okay.
And, but I understood your answer. It's a justifiable method. So since we have this figure here on display, I have the opposite question of that Aion did. So because I put here in my notes, why can't you tell already that you have a pion decay bump? Because when you show me the shape of the curve of the leptonic process, and then which is pretty flat on the low energy side, if I'm on the left side, I think it's low energy. And then we have this, it's a parabola shape on the pion. For me, it was pretty clear that any test you do, we would favor the pion decay process. But you guys mentioned some statistics on data, and as well, Aion explained for us why Karl Popper cannot be used, because we can always tweak our models, and we can never, there's no falsibility possible in several cases. So we can do a leptonic model that have this shape as well, if I understood correctly.
Yeah.
Is that the case?
Yeah.
Did I understood correctly?
Yeah, and sure. Well, when I was not 100% confident that we were seeing a pion decay bump, I was talking about the systematics. We have 2 assets, the systematics here, that are going to be a little bit larger than, their error bars are going to be a little bit larger than they are here, and maybe it's not going to be, we will not be able to point for a hadronic bump. So
if you are able to build a covariance matrix for this data that takes into account systematic effects somehow, I don't know exactly the process, but I'm familiar with other processes that we can take the systematic correlations between data which are supposed to be independent or things like that into a covariation matrix that relates them. Then you can do your model procedure, and you can use any model comparison that will tell how much one model is favored in comparison to another. And that tells you a number, that then you interpret the number. If depending on the number, you have a clear-cut definition, or both of them are equally likable, and things like that. So I think you have to explore this data, because you might be solving you might be favoring strongly one model in favor than the other. Okay, so still talking about this, you mentioned in the introduction that this process could have been done by relativistic protons or non-relativistic protons, right?
Well, I don't remember if I said both, but okay, energetic protons, yeah.
But can you tell something about the property of this proton population from this data?
Yes, you can. Well, you would have to model. It would be a little bit model dependent, but yeah, you can tell. You can tell, for instance, the energy of the distribution of the protons. You could use the shape and the maximum of the SED to get information about the protons. Yes, I didn't try to do this. I'm not sure exactly what exactly we can get from the protons, but we can have results about the energy distribution of the protons by using the SED. Yeah.
I think you should then. Seems.
But we didn't try to do this. Okay, it's something that we didn't do.
Can be the paper. Yeah. So in your one of the final chapters, you made a cartoon that explains why the higher energy centroids of the distribution are closer to the black hole and the low energy ones are further away, right? So
yes, I'm going to show it, but go ahead.
Yes. Okay, so maybe I missed something. So are we assuming that the emission have a preferential direction? Because all these points are kind of aligned. The red, the blue, and the central one are aligned, or is that jet thing? Is what's going on?
Yes. Well, first of all, this is a very, very naive exploration of our data. Yes, what I should have included in this slide, but if you remember that slide with the position of the source, we can see that the source is closer to Sagittarius A star in higher energies than as it gets to lower energies, it starts to get farther away from Sagittarius A star.
And all in the same side.
All in the same size, almost following a straight line. Okay, almost, not exactly. And since I had the light curve of the sources, what I was wondering is, okay, I have the light curve of the sources. Maybe there is something happening here that is similar to that X-ray echoes that I showed you, which are caused by some events from Sagittarius A star that released X-rays, and as their X-rays are traveling through the molecular clouds, the molecular clouds starts to light, okay, in response to the X-rays. And I said, maybe we could just consider this hypothesis here very naively, because as we said several times here, the light curves were not showing some variability that we could try to correlate to each other, to one another, or to some flare or things like this. But this, I was considering something like this. For instance, there is a molecular cloud, and the cosmic rays that are interacting with this cloud are traveling through the cloud and things like this. This is what we were trying, but it is very naive. I was just trying to take advantage of the fact that we had the position of the emission and the light curve. So, yeah.
Well, that was my last question. Many congratulations, Fabio.
Thank you very much.
A piece of work. Many congratulations, Rodrigo. And thank you both again, because I could learn a lot of things that I don't see in my everyday. Thank you.
Thank you. Thank you very much, Edu. Can you hear me? I think you You can hear me okay?
Yeah.
Okay. Bem, first in Portuguese, now the announcement then in English. Todos os membros da banca tiveram a oportunidade de perguntarem sobre o trabalho ao candidato. A banca agora vai se reunir numa sala privada, virtual, para discutir o trabalho do candidato, discutir a tese em privado. E nós retornaremos a esta sala pública em cerca de 10 a 15 minutos para anunciar o resultado da defesa do candidato. Now in English, so all members of the thesis committee, we had the opportunity to ask questions about the work of the candidate. The thesis committee will now convene at a private online room for discussing the PhD thesis work, and we will meet back in this public room in about 10 to 15 minutes to announce the result of the candidate's defense. Okay.
Você pode colocar o link para outra sala? Ok.
Oh.
Hello.
Hello, Fabio.
Olá.
Olá. So I imagine the audio is working. Okay, so the audio is working fine. Okay, so as usual, begin with the Portuguese, then well, we'll begin now with the English, and then finish with the Portuguese announcement. So I'm happy after convening with committee members in the private room. I'm happy. I'm thrilled to announce that the candidate has been approved with unanimity for the PhD degree. Gostaria de anunciar que o candidato, depois de deliberar com os membros da banca na sala privada, todos nós concordamos por unanimidade, o candidato está aprovado para o doutorado. Parabéns, Fábio. Congratulations.
Obrigado. Thank you. Thank you very much.
Fabio, you need to check whether or not you are the first one doing the whole career.
I'll check. It is a badge of honor if I'm the first one.
No, I think you are.
Great.
Yeah, that's a historical moment.
Yeah. Thank you all. Thank you. What I said at the beginning is true. Every time I talk to any one of you, and of course Rodrigo also, you always help me a lot. Thank you very much.
Yeah, thank you to all the committee members again. Thank you for participating. Thank you. Yeah.
Okay. Thank you. Thank you all for staying with us for so long. I hope it was interesting, and thank you very much. I tried to make it interesting. I don't know if I could, but I tried. Wow.
Yes, please, Richard, please. I took a screenshot,
nice.
but I don't think I appear in the screenshot. So if you could do that, I will ask everybody to smile, a big smile, a big happy smile, especially Fabio.
Fabio looking very tired.
Yeah, I am.
Wave.
Wave.